Well, this problem introduces a new layer of complexity because this rocket is now fired at an angle. And so it's not true anymore that the vertical dimension has no initial velocity. In fact, this rocket is blasted off so that it does have both a horizontal and a vertical velocity. Well, let's figure out how to solve this. The first question that we're asked here is, what is its initial vertical speed? Well, let's model the rocket's velocity by drawing a vector. Velocity is a vector quantity. And it's telling us that the velocity, the overall velocity of this rocket is 30 meters per second. And it's also telling us that this is shot up from an angle of 70 degrees above the horizontal. So what we want to do here is figure out what is the component of the velocity that's in the horizontal direction. So we'll take this overall velocity and we'll divide it into two vectors, like we've done many times before, resolving this velocity vector into two components. The horizontal velocity is adjacent to the 70-degree angle, so the horizontal velocity is going to be equal to 30 meters per second, the overall speed, times the cosine of our 70-degree angle. And that turns out to be 10.3 meters per second. And since we're assuming that there's no wind resistance, that's going to be a constant velocity. Throughout the entire flight, the velocity of the rocket is going to be 10.3 meters per second in the horizontal. In the vertical is a different story. The vertical is a different story, however, and so we want to find out the initial vertical velocity, but it will be changing, we know, as the rocket slows down going upward and then comes down and accelerates. Well, the vertical component, VV I'll call it, and I think I'll call it VVI for initial because we know this is going to eventually change. Well, that's going to be, because it's opposite the 70-degree angle, equal to our 30 meters per second times the sine of the 70-degree angle. And that turns out to be 28.2 meters per second. That's a starting velocity. That'll change. The horizontal, we have a velocity that isn't going to change. The next question we're asked here is, what height will the rocket reach? And we've actually figured out this some time ago. We know how to do this kind of a problem because we've done it in the past when we were considering only one-dimensional motion. So here's what we know about this flight. The rocket's going to go up and it's going to come down. We want to know how high it got during that change, and we'll call that D. We know what its initial velocity was, VI in this direction, is 28.2 meters per second. When it reaches the top of its arc, we know what its final velocity is. VF is going to be 0. So if we want to know what D is, well, we have a relationship for that. It's one of the two relationships that govern constant accelerated motion. And that's this. Final velocity is equal to the square root of initial velocity squared plus 2 times A times D. Well, in this case, final velocity is 0. Well, D is what I'm trying to find here, and this problem is made simpler by the fact that VF is 0. So we could rewrite this and we could say VF equals 0, and 0 is equal to the square root of VI squared plus 2 times G times D, because it's accelerated due to gravity. Well, if I square both sides, 0 squared is still 0, so that means 0 is equal to VI squared plus 2 times G times D. Well, that means that VI squared is equal to the negative of 2 times G times D. So what I'm trying to find here is D, so I'm going to solve for D by dividing both sides by negative 2G. So D is equal to VI squared divided by negative 2 times G. Now I'll just put my numbers in here. We decided in the last problem, we figured out that 28.2 meters per second was the initial vertical velocity. We have to square that. And then we're going to divide by negative 2 times the acceleration due to gravity. If we're calling the initial velocity positive 28.2, then we have to call G negative 9.80, and that's meters per second squared. Now, if we look at what's happening to the units here, we're squaring meters per second on the top. That gives us meters squared per second squared. We're dividing by meters per second squared. The only thing that doesn't cancel out is meters, so we have a nice distance unit. It turns out that 40.5 meters is the height that it will attain. Well, the next question we're asked is, how long will it be in the air? So we're looking for how much time is it going to spend in the air. Going back to our problem-solving page here, we now know what d is, and we know the equation that governs time, that relates time to distance during an acceleration, which is what we've got here. So let's make use of that. We know that distance is equal to initial velocity times time plus acceleration over 2 times time squared. Now, there's an easier way and a harder way to solve this problem. In fact, there are several ways to do this problem. This is a quadratic equation. We know distance, we know the initial velocity, we know the acceleration is equal to g, and we can plug all that stuff in here and create this quadratic equation. And there are several ways to solve it. You can graph with your graphing calculator. You can use your graphing calculator's solver function. That's another thing you can do. There is another trick too. There's an actual quadratic equation feature on most of your graphing calculators. However, there's a trick too that will make this even easier. If we go back and look at our picture and remember what we learned in the rocket lab, we know that the time it takes to go from the bottom of the flight up to the top is the same as the time it takes to go from the top of the flight down to the bottom. And finding that time will actually be easier. We just double that and we'll have the total time of flight, the time it takes to go up and the time it takes to go down. So here's what I'm going to do. I'm going to assume that I'm at the top of my arc and that my initial velocity is 0 before it begins to fall. My acceleration is going to be g, and I know it's going to fall through 40.5 meters. So here's how I can get this. Actually, what I'm looking for is delta t. So I'll take d is equal to g over 2 times delta t squared, and I'll solve it for delta t. So 2 times d divided by g is delta t squared. The square root of both sides then is going to give me delta t. So the time it spends during half of its flight, the fall, is 2 times 40.5 meters divided by 9.80 meters per second squared. When I take the square root of that, I'll have my answer. And the square root of 1 over seconds squared is just going to be seconds. So when I multiply 2 times 40.5 and divide by 9.80 meters per second squared, what I come up with is 2.87 seconds. So that means the total flight time is going to be double that, because this was just the time it took to fall. We know it will take an equal amount of time to rise up to the top of the arc. So 2.87 seconds doubled comes out to 5.75 seconds. There are other ways to do this, as I mentioned before. And if you'd like to know more about that, see me and I can show you how to use your graphing calculator or a good old-fashioned quadratic formula to figure your answer out. But I think this shortcut, it makes life a lot easier. Our next question is, how far away from the launch site will the rocket land? So looking at a model of our flight here, what we're trying to find is, what is this distance from here to here? That's what we're interested in. Well, what we know about projectile motion is that the motion in the horizontal direction is constant speed motion, unless you have wind resistance, which we're ignoring here. So based on that, the distance covered here in the horizontal should just be equal to the horizontal velocity times the time of flight. But we know, we calculated earlier, that the horizontal velocity is 10.3 meters per second. So the distance covered here is going to be 10.3 meters per second, that velocity, times the total time that it was in the air. Well, it was in the air for 5.75 seconds. We calculated that just a bit ago. So when you multiply these two together, the seconds are going to drop out, and you get a distance in meters, and that distance is 59.2 meters.